Hello and welcome to this revision session for AQA A-Level Physics, Paper 1, looking at the topic of waves and the concept of progressive waves. So in today's revision session, if we've been successful and we've learned today, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? Well, when you're completing your revision session, divide your piece of paper into two sections. Make the section on the left-hand side larger than the right-hand side. And in this left-hand side section, what you should be doing is writing down your working out and answers to the questions in this revision session. And when you're doing this, make sure you write your answers in full sentences and show your full working out. Whilst on the right-hand side, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, you should write up these notes into a revision sheet for you to use independently. So how should you be revising for your A-Level Physics? Well, the first step is to learn the key facts. Use revision guides, class workbooks, student prep nooks and a knowledge checker to learn the key ideas of the course. Now you may wish to make mind maps or to write out the notes yourself. Secondly, test yourself. Use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. Then use exam prep books, homework books, study books and additional workbooks to answer exam questions and to mark your own work. Now you may wish to download your own exam past papers to do this. So your 3 steps of learn the key facts, testing yourself and practicing exam style questions are how you can prepare for your A-Level Physics examination. So let's have a look at what questions we're going to be using in our papers today. There'll be 2 types of questions we want to use. Firstly, general checker questions, basic questions designed to probe your understanding of the key concepts of the topic. Then we'll be looking at assessment point questions. These are past paper examination questions which will mimic the types of questions found in public examinations. So let's start with our general checker questions. What type of wave is this and how can you tell? So pause the video now, then unpause the video when you want to go through your answer. Well, this wave is a progressive wave. As energy is being transferred, the wave is a transverse wave as the propagation is at right angles to the oscillation. In which direction is the particle at A moving? Pause the video now, then unpause the video when you want to go through your answer. By reviewing the wave pattern and how the wave pattern is moving across the particles, you can see that the particle at A will be moving downwards. The next question, in which direction is the particle at B moving? So pause the video now, then unpause the video when you want to go through your answer. Again, by looking at how the wave pattern is moving, the particle at B will be moving upwards. The next question, what is the amplitude of this wave? Pause the video now, then unpause the video when you want to go through your answer. Again, you've got to understand the definition of amplitude. Amplitude is from equilibrium to the peak or the trough of the wave, so it's half of 7.50, 3.75 millimeters. Figure 7 shows a continuous progressive wave on a rope. There is a knot in the rope, the wave travels to the right. Describe how the vertical displacement of the knot varies over the complete cycle. So pause the video now, then unpause the video when you want to go through your answer. Once again, you've got to imagine the wave pattern travelling through the particles and causing them to oscillate. So it will go vertically downwards, so it will be a quarter cycle to the maximum negative displacement, then upwards again, a quarter of a cycle back to equilibrium, then another quarter of the cycle back to positive displacement, and then back down again, so another quarter of the cycle to equilibrium position or zero displacement. Now, the continuous wave of the same amplitude and frequency moves along the rope from the right and passes through the first wave. The knot becomes motionless. Explain how this could happen. So pause the video now, then unpause the video when you want to go through your answer. Well, a stationary wave will have been formed by superposition or interference of the 2 coherent progressive waves. Now the knot must be sat at a node, as the waves will always cancel where you've got the knot and there's node. Okay, so there's a node displacement and no oscillation there. Figure 6 represents a progressive wave travelling from the left to the right on a stretched string. Calculate the wavelength of the wave. So pause the video now, then unpause the video when you want to go through your answer. You should identify that the distance of 0.50 meters represents 1 1/4 waves. So 1 1/4 of 0.5 will equal us to be 0.40 meters. The frequency of the wave is 22 Hz. Calculate the speed of the wave. So pause the video now, then unpause the video when you want to go through your answer. So, how do you work out the speed? The speed is equal to frequency times by wavelength. So it's 22 times by 0.40, that's the wavelength of the wave, which equals 8.8 meters per second. On this wave, describe how the displacement of point Y on the string varies in the next half period. So pause the video now, then unpause the video when you want to go through your answer. Now again, you've got to imagine the wave pattern travelling through the particles as it moves across in the direction of the wave travel. So what you can see is that position Y, it'll be at a position of maximum, at a quarter of the period or the cycle, and then it'll return back to its original position in the next half period. You can see that it's going to be moving upwards because you can see that the maximum is pushing upwards on that particular wave pattern there. Next question says, what is the path difference between points A and C? So pause the video now and then unpause the video when you want to go through your answer. So that's going to be half a wavelength because you can see A and C are separated by half a wavelength, okay, when you look at your wave pattern. So what is the path difference between A and D? So pause the video now and then unpause the video when you want to go through your answer. Right, so our answer here is going to be 0.75 wavelengths. Next question, what is the path difference between points E and K? So pause the video now and then unpause the video when you want to go through your answer. Our answer is either 1.5 wavelengths, or you would say half a wavelength, because it can reset after a wavelength because the overall displacement from the initial is half a wavelength. What is the path difference between D and L? So pause the video now and then unpause the video when you want to go through your answer. Right, the answer is 2 wavelengths or 1 wavelength. The next question says, what is the path difference between C and J? So pause the video now and then unpause the video when you want to go through your answer. It will be 1 3/4 wavelengths or 3/4 wavelength. What is the phase difference between point A and E in degrees? So pause the video now, then unpause the video when you want to go through your answer. The answer is 360 degrees, as it's one whole wavelength between the two, but also it could be interpreted as 0 degrees because it resets after every wavelength. What is the phase difference between points B and K in degrees? So pause the video now and then unpause the video when you want to go through your answer. The answer is either 810 degrees, or if you reset after every 360 degrees, 90 degrees. What is the phase difference between points F and L in degrees? Pause the video now and then unpause the video when you want to go through your answer. The answer is either 540 degrees or 180 degrees. The next question says, what is the phase difference between points C and H in degrees? So pause the video now and then unpause the video when you want to go through your answer. The answer is 450 degrees or 90 degrees. What is the phase difference between points D and I in degrees? Pause the video now, then unpause the video when you want to go through your answer. The answer is 450 degrees or 90 degrees. What is the phase difference between points A and D in radians? Pause the video now, then unpause the video when you want to go through your answer. The answer is 1 3/4 pi radians. Now remember, there are 2 pi radians in every wave cycle. So between A and D, which is going to be 3/4 of a wave, we can therefore see that it's going to be 1 3/4 pi radians. What is the phase difference between A and E in radians? So pause the video now, then unpause the video when you want to go through your answer. The answer is 2 pi radians or 0 pi radians because it resets after every 2 pi radians. What is the phase difference between B and F in radians? The answer is 2 pi radians or 0 pi radians. What is the phase difference between points E and G in radians? When you look on here, it's going to be half a wavelength, so that's 1 pi radians. What is the phase difference between points E and L in radians? Pause the video now, then unpause the video when you want to go through your answer. The answer is 1 3/4 radians. The next question says, what is the phase difference between points A and M in radians? So pause the video now and unpause the video when you want to go through your answer. The answer is either 6 pi radians, 2 pi radians, or 0 pi radians. What is the phase difference between points C and I in radians? So pause the video now, then unpause the video when you want to go through your answer. The answer is either 3 pi radians or 1 pi radian. The next question says, the light incident on the camera lens is unpolarized. The photographer places a polarizing filter in front of a lens. Explain how the polarizing filter affects the light incident on the camera lens. So pause the video now, then unpause the video when you want to go through your answer. Well, when we look at this answer, unpolarized light oscillates in many different planes. Now, the light perpendicular to the plane polarization of the filter is absorbed, or only the light parallel to the plane of polarization of the filter is transmitted. So this tells us that the polarized light will only oscillate in one plane, so therefore our light intensity is reduced. The next question says, state what is meant by unpolarized light and describe how you can determine using a polarizing filter whether a light source is giving out polarized or unpolarized light. So pause the video now, then unpause the video when you want to go through your answer. Now, in unpolarized light, vibrations are in all directions, at right angles to the direction of travel, and the sequence of directions is random. Now, to distinguish this, viewing light through a Polaroid and rotating it can be used. So light is unpolarized if the intensity doesn't depend on the angle of the Polaroid. Now, light is polarized if it does depend on the angle of the Polaroid. The Polaroid will decrease the intensity of the unpolarized light, so for polarized light there are 2 angles of extinction per turn of the Polaroid. They tend to be when it's going to be at 90 degrees and 270 degrees. Next question, explain why sound waves cannot be polarized. So pause the video now, then unpause the video when you want to go through your answer. So sound waves are longitudinal waves. So since oscillations are parallel or the same direction to wave travel, it tells us that they cannot be polarized. Next question, explain why polarized sunglasses will help find a person fishing to see fish more clearly. So pause the video now, then unpause the video when you want to go through your answer. Reflected light is polarized, so the intensity of light reflected on the water will be reduced by the polarizing filter. The next question says, figure 2 shows the displacement of a string as the wave travels along the string. Give the amplitude of the wave. Give the wavelength of the wave, and a different transverse wave has a wavelength of 1.8 meters and a frequency of 16 Hz. Calculate the speed of this wave. So pause the video now, then unpause the video when you want to go through your answer. So the amplitude is from equilibrium to the peak or the trough, so that will be 19 centimeters. The wavelength is the length of one whole cycle, which is 80 centimeters. And the speed of this wave is going to be frequency times by wavelength, 16 times by 1.8, 29.0 meters per second. The next question says, figure 1 shows the displacement of a surface water wave with time. Identify the number of oscillations shown in figure 1. Give the amplitude of the surface water wave shown in figure 1 and give the period of the surface water wave shown in figure 1. So pause the video now, then unpause the video when you want to go through your answer. Right, how many oscillations do we have in figure 1? Well, you can see the wave pattern is repeated 2.5 times. The amplitude is from equilibrium to the peak, which is going to be 8 centimeters, and our period is the time taken for one whole complete wave, which is 20 seconds. A student is wearing polarizing sunglasses observes a mobile phone screen. The student rotates the mobile phone through 90 degrees as shown. The screen then appears to completely black. Explain why the screen appears completely black when the student rotates the mobile phone through 90 degrees. So, pause the video now, then unpause the video when you want to go through your answer. Right, so what can we say? Well, light emitted from the mobile phone screen is going to be polarized because it's affected by the angle of the Polaroid. So when the phone is rotated, the plane of polarization of the light and the plane of polarization of the polarizing filter in the sunglasses are perpendicular when the phone is rotated, and then the polarizing filter on the sunglasses will absorb the light. So let's now have a look at some examination style questions. So a research group is studying water waves travelling across a still lake. Further observations reveal a wave passes a stationary buoy causing it to oscillate with a period of 1.6 seconds. State what is meant by a progressive wave and describe how the particles of the water move as the wave passes. Determine the wavelength, frequency and speed of the wave. 2 points P and Q are separated by 0.20 meters along the direction of wave travel. Calculate the phase difference between the oscillations of P and Q, expressing your answer in both radians and as a fraction of a full cycle. Then researchers suggest that the energy is transferred by the wave, but that the water itself does not travel across the lake. Explain how the progressive waves transfer energy without the net transfer of matter. So pause the video now, then unpause the video when you want to go through your answer. Okay, in this first question, a progressive wave transfers energy through a medium without transfer material between points. Particles in the medium will oscillate about fixed equilibrium positions, and in a surface water wave, the particles will move in circular or elliptical orbits as the wave passes. Now, the oscillation is going to be local. The waveform moves, not the medium. We can see the wavelength from the diagram. It's 0.80 meters. The time period is given in the question 1.6 seconds. The frequency is 1 over the time period, 1 over 1.6, so 0.625 hertz. The speed is frequency times by wavelength, so therefore it's 0.50 meters per second. Now the difference between P and Q is 0.20 meters. So as a fraction of the wavelength, that's 0.2 over 0.80, so it's 0.25. So therefore the phase difference is a quarter of a full cycle. Now in radians, we know a full cycle is 2 pi radians, so therefore the phase difference is pi over 2 radians. Now particles will oscillate about fixed points, but they don't experience a net movement over a complete cycle. The energy is carried by the oscillations propagating through the medium, not by the movement of the material itself. The next question says a sports science team investigates how water waves behave at a surfing competition. They set up a monitoring station on the beach and record the following data for a series of incoming ocean waves. Later, they measure the speed of the surfers relative to the water as approximately 2.5 meters per second when catching a wave. The team notices that the waves are steeper and break more easily closer to the beach, where the water depth is much shallower. Calculate the speed of the progressive waves as they travel towards the beach. Compare the speed of the waves with the typical speed of the surfer, and discuss whether a surfer will be able to catch and ride the waves based on these speeds. Explain why waves break more easily in shallow water in terms of changes to wave properties such as speed, wavelength and amplitude. Then evaluate 2 practical challenges that the team would face when collecting accurate wave data in a real sporting event at the beach, and suggest how they could minimise these errors. So pause the video now, then unpause the video when you want to go through your answer. Okay, so how do you calculate the wave speed, the speed? So we know that v is going to be equal to lambda over t, so it's 14 over 7, so it's 2.0 meters per second. Now the wave speed is 2 meters per second, the surface speed is 2.5 meters per second relative to the water. So to catch a wave, the surfer must match or exceed the wave speed relative to the ground. Now since the surface speed is greater than the wave speed, they will be able to catch and ride the wave. Now in shallow water, the wave speed decreases because the wave interacts with the seabed. As the speed decreases, the wavelength shortens and the wave height, the amplitude increases. This increased amplitude causes instability, leading the wave to steepen and eventually break. Now in the next one, the variable environmental conditions like the tides and the winds will make the time and distance measurements less reliable. The challenge is that the visual measurements from the shore are subject to parallax errors, to human reaction time errors, so using automatic wave sensors and GPS timing and positioning equipment perpendicular to wave motion will help minimise these errors. A new city communication network is being designed, which will rely on both optical and radio wave technologies. Engineers are discussing the orientation of aerials for radio wave transmission and the use of polarizing filters for optical communication safety systems. During the design meeting, the following claims are made. Claim 1. Polarization does not prove that electromagnetic waves are transverse, because particles in a longitudinal wave could also align in a single plane. Radio wave aerials will transmit equally well regardless of how the transmitting and receiving aerials are aligned. Claim 3. Using polarizing filters with optical signals can help prevent interference from sunlight. So explain why the phenomena of polarization provides strong evidence that electromagnetic waves are transverse in nature. Critically assess Claim 1 made by the engineers. Explain the physical reason why radio wave aerials must be correctly aligned for maximum signal transmission, referencing the properties of electromagnetic waves. Then evaluate the claim about using polarizing filters to reduce interference from sunlight in optical communication systems. So, pause the video now, then unpause the video when you want to go through your answer. Okay, in the first one, polarization involves restricting the oscillations of a wave to a single plane. Now, only transverse waves can have oscillations perpendicular to the direction of energy transfer. Longitudinal waves will oscillate parallel to the direction of energy transfer and therefore cannot be polarized. So, observation of polarization is direct evidence that electromagnetic waves are transverse. Now, claim 1 is incorrect because in longitudinal waves, oscillations will always be along the direction of travel. No transverse oscillation plane will exist for a longitudinal wave, so it can't be restricted by polarization. Therefore, polarization can only indicate transverse oscillation, not longitudinal. Next one, radio waves are electromagnetic waves. The electrical field oscillates in a particular direction. The areals must align with the electrical field oscillations to effectively transmit and receive signals. Misaligned areals result in reduced signal reception or even complete cancellation if there is a misalignment of 90 degrees between the areal and the field. So therefore, the correct orientation is critical for efficient transfer in radio communications. Now, sunlight is largely unpolarized, with electrical fields vibrating in many different random directions. Reflected sunlight often becomes partially polarized, predominantly in the horizontal directions. So our polarizing filters will align vertically, then they can block out much of this horizontally polarized reflections, improving our optical communication signal clarity. So therefore, this claim is correct. Polarizing filters can effectively reduce interference from light sources. During an earthquake, two types of seismic wave are detected by monitoring stations, P waves and S waves. P waves are detected first, followed by S waves a few minutes later. Engineers analysing earthquake data observe the following properties. So the seismologist uses information to help locate the earthquake's epicenter and infer properties about the Earth's interior. So, identify which types of wave, P waves or S waves, is longitudinal, which is transverse. Explain your reasoning with reference to the displacement of particles relative to the direction of wave propagation. Discuss how the difference in speed in P waves and S waves can be used in monitoring stations to estimate the locations of different earthquake epicenters. Then explain, using the nature of wave motions, why the P and S waves arrive at monitoring stations at different times, even though they're generated by the same earthquake event. Then evaluate how the study of seismic waves has contributed to the understanding of the Earth's internal structure compared to early models that assumed the Earth was completely solid. So, pause the video now, then unpause the video when you want to go through your answer. Right, so let's go through the answer to this particular question. Now, P waves have a particle displacement parallel to wave direction, so therefore they're longitudinal. S waves have a particle displacement perpendicular to wave direction, so are transverse. In longitudinal waves, you get compressions and rarefactions occurring along the direction of energy propagation. In transverse waves, oscillations are perpendicular to the direction of energy transfer. Next, P waves travel faster than S waves and therefore arrive earlier at monitoring stations. The time difference between P and S wave arrival increases with distance from the epicenter. Now, by measuring the different time differences at multiple locations and distances from each station can be easily determined. Now, using triangulation from several stations, the epicenter location can be located and calculated accurately. Now, P waves are longitudinal, whereas oscillations are parallel to wave propagation. Now, S waves are transverse, where the oscillations are perpendicular to propagation direction. Now, longitudinal waves typically travel faster through solids than transverse waves. So therefore, the P waves will arrive first, followed by our slower S waves. Now, seismic studies show that S waves stop at the outer core, revealing that they must be a liquid. Now, P wave speeds changes indicate different layers with varying densities and states: solid inner core, liquid outer core, solid mantle. So our modern Earth models recognize layered internal structure rather than the assumption which we earlier had of a completely solid Earth. Now, a physics research team is investigating stationary waves in 3 different experiments. Experiment A, a stretched string fixed at both ends vibrating in different modes. Experiment B, microwaves reflected between 2 parallel metal plates. Sound waves trapped between 2 waves forming an acoustic standing wave. In experiment A, the following measurements are taken for the first harmonic. Explain how stationary waves are formed in each of the 3 experiments. In your answer, refer to the superposition of wave travelling in opposite direction. Sketch a labelled diagram showing the displacement pattern of the string vibrating in the second harmonic. Label all the nodes and antinodes. Using the data for experiment A, calculate the frequency vibrating at the first harmonic. Discuss why in experiment B the maximum electrical field strength is not observed exactly at the metal plates but instead occurs at some distance away. Then evaluate the usefulness of the stationary wave model for describing real sound waves in a room. In your answer, consider the strengths and limitations of the model. So pause the video now, then unpause the video when you want to go through your answer. Right, so in our first one, stationary waves form with two waves which are coherent, so identical frequency, amplitude, and constant phase difference travel in opposite directions and superpose. So on the string, the reflections of fixed end cause the incoming and reflected waves to superimpose, creating nodes and antinodes. In microwaves, the electrical field waves reflect between the metal plates, forming standing electromagnetic waves with nodes and antinodes. In sound waves, the pressure variations of the sound wave reflect off the walls, superposing to form stationary sound patterns of pressure nodes and antinodes. Next question, a correct sketch of a string with a node at each end and one node in the centre with two loops. You label your nodes, your zero displacement points, and your antinodes, your maximum displacement points. It should be symmetrical with half a wavelength fitting between through the nodes, as shown. Now in our next question, we know F is equal to 1 over 2L times by the T over the mass per unit length. So it's a half times by 0.75 over the square root of 20 over 1.2 times 10 to the minus 3, so it's 86.1 Hertz. Now in metal surfaces, the boundary conditions will force the electrical field to be a node, because at the ends of both of the wave pattern there must be nodes. So the maximum field strength, the antinodes, occurs halfway between the nodes, but not at the plates, but at distances corresponding to quarter wavelengths away. So therefore our maximum field is observed in the middle of the cavity, not at the surfaces. Now, stationary wave models can explain things such as resonance, room harmonics, and the standing sound waves that occur at particular frequencies, which leads to acoustics. But in real rooms, walls are not perfect reflectors, and some absorption and scattering can occur, distorting ideal stationary wave patterns. So whilst useful for predicting dominant resonances and the stationary wave model must be adjusted for real-world conditions involving imperfect reflections. A violinist notices an unusual pattern during a concert rehearsal. One of the strings produces a noticeably lower pitch than usual, even though its length appears unchanged. The maintenance technician has checked the string and notes the following. The tension of the string has decreased slightly after transport. The mass per unit length of the string is unchanged. The string is designed to operate in a second harmonic mode during performance. The violin string has a length of 0.35 meters. Later, the technician adjusts the tension back to its intended value and retunes the string. When plucked, the string now vibrates cleanly and a frequency of 440 Hz is detected for the second harmonic. The technician wants to ensure that the first harmonic would correspond correctly to the design specification for the material used. Explain, without calculation, why a decrease in tension will cause the pitch of the string to lower. Use the information provided to determine whether the original first harmonic frequency for the string would meet the design requirement of 220 Hz. Describe the form of the stationary wave pattern when the string vibrates in the second harmonic, clearly indicating the position of nodes and antinodes. Then critically evaluate whether adjusting the string length rather than the tension would have been a better approach for correcting the tuning problem. So pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, lowering the tension reduces the restoring force acting on the displaced particles of the string. The reduced restoring force lowers the speed of the wave propagation along the string. The lower wave speed results in a lower frequency for a fixed wavelength, so you'll get a lower pitch. Now in the second harmonic, we know that it's going to be double the first harmonic. Now given that F2 is 440 Hz, F1, the first harmonic, is 220 Hz. 220 Hz matches the design requirement, therefore the correctly tuned string meets the specification. In the second harmonic, there's a node at each end of the wave pattern and a node and an antinode and a node also at the center of the string. Two loops will therefore form, each loop with an antinode at its center. The string length is equal to exactly one full wavelength. Now, What you can do is adjusting the string length would alter the wavelength of the standing wave. Shortening the string increases the fundamental or first harmonic, raising the pitch. However, changing the length affects the physical feel and playing characteristics, so therefore musical design expects certain lengths, so adjusting the tension keeps these physical properties unchanged. Now additionally, adjusting string length risks upsetting harmonic tuning and resonance with other strings, so adjusting the tension rather than the length is a better, more musically consistent solution for correct tuning. In an experiment, microwaves are emitted into a rectangular metal cavity. One end of the cavity reflects microwaves completely, while the other end has a partially reflective mesh, allowing some microwaves to enter but also reflect back. The cavity is designed to create a stationary wave at specific microwave frequency. Measurements show that the distance between two adjacent points of minimum microwave intensity inside the cavity is 1.5 centimeters. The experiment uses a microwave source operating at a frequency of 10 GHz. During a discussion, a student argues the stationary wave forms because two waves with different frequencies interfere. This spacing between adjacent minima represents a full wavelength of the microwave. Increasing the frequency would increase the distance between adjacent minima. Using the information provided, explain carefully why a stationary wave forms in the cavity and why the waves involved must have the same frequency. Analyze the distance between the adjacent minima observed in the cavity, deduce the wavelength of the microwaves, and explain your reasoning clearly. Assess Claim 2, made by the student, regarding the relationship between adjacent minima and the microwave wavelength. Evaluate Claim 3, made by the student. In your answer, consider the mathematical and physical relationships involved. So, pause the video now, then unpause the video when you want to go through your answer. Okay, in the first one, a stationary wave forms when two waves with the same frequency are travelling in opposite direction. Superposition occurs, producing constant regions of constructive and destructive interference. The reflection from the cavity surfaces ensures a coherent reflected wave. Now, different frequencies would lead to a non-constant phase difference, causing moving beats but not a stationary wave pattern. The next one, the distance between adjacent minima correspond to half a wavelength, so therefore the wavelength is going to be 2 times by 1.5 centimeters, which is 3 centimeters. So adjacent minima occur at wavelength over 2, lambda over 2 spacing in a stationary wave. Now claim 2 is incorrect. The distance between adjacent minima is half a wavelength, not a full wavelength, so in stationary waves the nodes are separated by lambda over 2. Now claim 3 is also incorrect. From the wave speed equation v equals f lambda, increasing the frequency f would decrease the wavelength lambda. Therefore the spacing between minima would decrease, not increase. So the claim misunderstands the inverse relationship between frequency and wavelength when the wave speed is constant. A company designs outdoor wireless optical communication systems that use a laser beam to transmit data between two tall buildings across a city. To reduce noise and unwanted signals, polarizing filters are installed at both the transmitter and the receiver. The system transmits light polarized vertically. During a routine test, the transmission system shows a much better performance on dry, clear days than foggy or rainy days. Technicians note that rotating the receiving polarizer by 90 degrees with respect to the transmitting polarizer results in no signal being detected, even though the laser remains switched on. One engineer suggests adding a second polarizer at the receiver set at 45 degrees relative to the transmitter's polarization direction to recover part of the lost signal in case of misalignment. Explain using the properties of transverse waves why the laser light used for data transmission can be polarized. Describe why no signal is detected when the receiving polarizer is rotated by 90 degrees, referring to the behavior of polarized light passing through a polarizer. Explain how inserting a polarizer at 45 degrees between two cross polarizers allows some light to be transmitted. Without using detailed formulae, describe qualitatively how the intensity of transmitted light will compare to the original laser beam. Suggest and explain why the system performs worse in rainy or foggy conditions even though polarization is unaffected. So, pause the video now, then unpause the video when you want to go through your answer. Now, electromagnetic waves are transverse. The oscillations of electric and magnetic fields are perpendicular to the direction of energy transfer. A polarizer restricts oscillations to a single plane of vibration. Only transverse waves can be polarized, longitudinal waves cannot. Now, a polarizer transmits only a component of light oscillating parallel to its transmission axis. When the receiver polarizer is rotated by 90 degrees, its axis is perpendicular to the incoming light's polarization direction, so therefore no component of the electrical field passes through. Our transmitted intensity is zero. Now, light polarized vertically passes into a 45-degree polarizer. A 45-degree polarizer allows part of the vertically polarized light through, since the light has a component aligned with the transmission axis. After passing through the 45-degree polarizer, the light is now polarized at 45 degrees. When this light reaches the 90 degrees horizontal polarizer, it again has a component alignment with that axis, allowing partial transmission. Overall, the transmitted intensity is significantly reduced compared to the original beam, but not zero, so some signal is recovered. Now, lastly, rain and fog introduce the scattering of light. Scattering is caused by wave droplets or suspended particles. Scattering sends light energy in many directions, reducing the amount reaching the receiver. Now, scattered light is often depolarized, but the main issue is intensity loss, not polarization. So the rain and foggy conditions cause attenuation of the transmitted signal, leading to a poor performance. Two different experimental setups are investigated. Experiment 1, a string experiment. A string is fixed at both ends and vibrated at one of its resonant frequencies, producing a standard wave pattern. Nodes and antinodes are observed along the string. The second experiment is a water channel experiment. Surface water waves are generated at one end of a long open water channel, producing waves that travel along its length. The following observations are recorded. In experiment 1, certain points along the string remain completely stationary over time. In experiment 2, all points of the water surface oscillate, but none remain permanently stationary. In experiment 1, the distance between two adjacent nodes is 0.40 meters. In experiment 2, the distance between two adjacent wave crests is 1.6 meters. The time for a crest to pass a fixed point in the channel is measured at 2.0 seconds. Describe two different key differences between the motion of the particles in the stationary wave and the progressive wave based on observations. Using the data of experiment 1 and experiment 2, determine the wavelength of the standing wave on the string and the wavelength of the speed of the progressive wave on the water channel. Explain why the energy is transferred along the water channel in experiment 2 but not on the string in experiment 1. And a student suggests that if the string experiment was performed badly, the pattern would no longer be fully stationary. Discuss the validity of the suggestion and use the wave principles to support your argument. So, pause the video now, then unpause the video when you want to go through your answer. In the first one, in stationary waves, some particles at the nodes do not move at all, but in progressive waves, all particles oscillate with the same amplitude pattern moving through space. In stationary waves, no net energy is transferred along the medium, yet in progressive waves, energy is transferred in the direction of wave travel. The distance between adjacent nodes is half a wavelength, so the wavelength of the string is 2 times by 0.40 meters or 0.80 meters. The distance between adjacent crests is a wavelength, so the wavelength of the water is 1.6 meters. The period of the water wave is 2 seconds. Frequency is 1 over time period, so it's 0.5 hertz. The wave speed is the frequency times the wavelength, 0.80 meters. In a progressive wave, energy is transported along the wave as the particles successively oscillate. In stationary waves, energy is stored in the standard pattern of oscillations, oscillate between kinetic and potential energy without any net transfer, so therefore no energy will move from one end of the string to the other in experiment 1. Now, a good reflection is essential for forming a stable stationary wave and ensures identical waves travel in opposite directions. A poor reflection means the returning wave may have reduced amplitude or a different phase difference, preventing a perfect superposition. So the stationary wave pattern will become unstable or disappear, so the student is correct. A student connected a signal generator to a loudspeaker and placed the loudspeaker near one end of a long tube containing sand. The student adjusted the signal generator until the sand collected in small heaps as shown. Explain why the sand collects in small heaps. The student determined the distance d between the centers of adjacent heaps. Describe the procedure she should follow to determine an accurate value for d. Assess whether the experimental data is consistent with the value for the speed of sound of 340 meters per second. Signal generator frequency 3.25 kHz. D 5.1 centimeters. So, pause the video now, then unpause the video when you want to go through your answer. In the first one, a standing wave is set up with the interference of sound waves taking place in the tube. When constructive interference occurs, the amplitude is a maximum. When destructive interference occurs, the amplitude is a minimum. Our sand is displaced from the antinodes to the nodes. Now we should measure it over multiple heaps to get a multiple distances, divide by the number of gaps, not the number of heaps, and then repeat the measurement and calculate an average. We know that the wavelength is going to be 2 times the distance, so it's going to be 0.120 meters, centimeters into meters. V equals F lambda, so you get 332 meters per second, but isn't the same as 340 meters per second. The photograph shows a stringed instrument called a cello being played with a bow. A standing wave forms on a cello string when the bow moves across the string. Deduce whether a thicker string will produce a note of higher or lower frequency compared with a thinner string. Assume each string is the same length and at the same tension. So, pause the video now, then unpause the video when you want to go through your answer. Right, we know that a thicker string will have a greater mass per unit length. We know V is approximately going to be equal to the square root of T over mu. So with V being smaller, we know that V is equal to F lambda. The wavelength is constant, but now our frequency must therefore change, so the thicker string will give the lower speed, so you must have a lower frequency. The speed of a wave on a string can be described with the relation V equals the square root of T over mu, where T is the tension in the string and mu is the mass per unit length of the string. A string of length 0.69 meters has a mass of 9.0 times 10 to the minus 3 kilograms. A wave is travelling along the string with a speed of 203 meters per second. Calculate the tension in the string. When a string is fixed at both ends and plucked, a stationary wave is produced. Explain in terms of superposition of waves how the stationary wave is produced. The string is vibrating at its fundamental or first harmonic frequency of 270 Hz and produces the stationary wave pattern shown in 9a. 9b shows the same string vibrating at a frequency called its third harmonic. What is the frequency of the third harmonic? So, pause the video now, then unpause the video when you want to go through your answer. In the first one, mu equals mass over length, so you work it through to be 9 times 10 to the minus 3 over 0.69. V equals the square root of T over mu, so we can rearrange that, pop the values in, T equals 450 newtons. Now how does it work? Well, waves reflect from each end, they interfere because they're coherent, creating maxima and minima. The third harmonic is the third multiple of the first harmonic, so it's 3 times by 270, 810 Hz. So that brings an end to our revision session in today's lesson. So if we've been successful, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics, and understand what topics we need to improve upon for A-level physics. So thank you so much for watching this lesson on progressive waves, which is a topic of waves in AQA A-Level Physics Paper 1. Thank you so much, and as always, have a lovely day.